Hi everyone. In this video, I am going to read Chemical Bonding, Covalent Bond. Theoretical treatment of covalent bond. The simple picture of covalent bond does not tell us anything about many interesting questions such as arrangement of electron in molecules, the shape of the molecular orbitals, energy levels in the molecules, etc. Like atoms, we can write the Schrödinger wave equation for describing the behavior of electrons in molecules. However, it is very difficult to solve the Schrödinger wave equation for molecules. This solution can only be obtained by using certain appropriations. There are two main approaches which are commonly used. First, valence bond theory. Second, molecular orbital theory. Variation principle. It is a mathematical technique to calculate the lowest energy state or also known as ground state of the system. The basic idea of the variation principle is that if psi is the wave equation for ground state, then the energy corresponding to this wave equation E naught is always less than associated with any other wave equation that might is proposed. In other words, no proposed or trial waves can have energy less than the true energy of the system. This method is illustrated below. The relation can be used to calculate the energy of the system by knowing the value of psi. Now suppose we guess a particular wave equation psi 1 which may not be correct wave function. Then the corresponding energy can be calculated by using the equation. Now let us guess some other wave equation psi 2 which can easily valence bond theory. The valence bond theory was put forward by W. Hilter and F. London in 1927. It was later improved and extended by L. Pauling and J. C. Slater in 1931. The basic assumptions of this theory are: first, atoms do not lose their identity even after the formation of the molecule. Second, the bond is formed due to the interaction of only the valence electron as two atoms come close to each other. The inner electrons do not participate in bond formation. Third, during the formation of the bond, not only the valence electrons from each bounded lose atom their identity, the other electron remains unaffected. Fourth, the stability of the bond is accounted by the fact that the formation of the bond is accompanied by the release of energy. The molecules has maximum energy at certain distance between the atoms known as internuclear distance. Larger the decrease in energy, stronger will be the bond formed. Valence bond theory. Formation of hydrogen molecule. Consider two hydrogen atoms Ha and Hb. When two atoms are far apart from each other so that there is no interaction between them, the wave equation of the system may be written as psi is equal to psi A psi B, where psi A is the wave function of Ha atom and psi B is the wave equation for Hb atom. When we bring the two atoms close to each other to form a covalent bond between them, then there will be interaction between them. The various interaction, that is the attractive interaction between nucleus of one and electron of second, and repulsive interaction between the nuclei Ha, Hb and electrons even E2. Using this equation, we can calculate the energy of H2 molecule as a function of internuclear distance. It may be noted that energy of the two isolated hydrogen atoms is conventionally taken as zero. It is clear from the curve that even the two atoms approach each other, the energy of the system start decreasing till a certain minimum value is reached. This stage corresponds to the formation of H2 molecule. The fall of potential energy is called as bond energy. The energy given by the fall of the potential energy comes out only 24 kilojoule per mole. The experimental bond energy for the formation of H2 has been found to be 458 kilojoule per mole. This has been shown by the dotted lines. Comparison of bond energy given by the curve 1 and experimental bond energy shows very poor agreement. Moreover, the minimum is found to be the internuclear distance of 0.90 Armstrong, whereas the experimental bond distance in the hydrogen molecules is 0.74 Armstrong. Evidently, the wave equation psi as calculated from equation 3 is not correct. This means that some interaction between the two hydrogen atoms have been ignored. The wave function was further improved to get the bond energy value comparable with experimental value. Some improvements are discussed below. First, exchange of ions. Second, screening effect of electrons. Third, ionic character of H and H bond. First, improvement exchange of electrons. As discussed above, the equation 3 has been obtained on the assumption that is electron of two hydrogen atom could be distinguished from each other. Therefore, the electron around nucleus A was labeled as 1 and that around nucleus B was labeled as 2. This assumption, however, is not correct. When the molecule is formed, it is not justified in labeling the electron because the two atomic orbitals overlap and the two electrons between indistinguishable from each other. We can no longer be sure that electron 1 will always be the near nucleus A and electron 2 will always near the nucleus B. In other words, the state in which electron 1 is near HV and the electron 2 is near nucleus HA is equally probable. In state 1, nucleus A is associated with electrons and nucleus B is associated with electrons second. In state 2, nucleus A is associated with electron 2 and nucleus B is associated with electron 1, where C1 and C2 coefficient which give the contribution of wave equation first and second respectively to the total wave equation psi. In case of hydrogen molecules, the two wave functions are equally probable and therefore they must contribute with equal weight as discussed earlier. The wave equation psi plus is called symmetric combination and wave function of psi negative is called antisymmetric combination. The calculation of energies associated with those wave functions psi 1 and psi negative are a function of internuclear distance as represented by curve second and curve third respectively. Inspection of figure 2 shows that energy curve second corresponding to wave equation psi positive has significant lowering in energy. Thus bonding is possible in this state. We may therefore regard it psi positive as a bonding state. The bond energies corresponding to this wave equation is 303 kilojoule per mole and the internuclear distance is 0.80 Armstrong. This value of bond energy is better than calculated from the wave function corresponding to equation 3. Thus, the wave function has been improved if the electrons on the atoms are exchanged. The additional lowering in energy for molecular orbitals as a result of the concept of exchange of electrons between hydrogen atom is called exchange energy. Thus, 303 minus 24 is equal to 279 kilojoule per mole is the exchange energy of hydrogen molecule. On the other hand, the plot of the energy of the system using the wave equation shows increase of energy as two atoms approach each other. This represents repulsive and non-bonding state. Thus, bonding is not possible in the antisymmetric combination. The symmetric combination of the atom results into bonding between atoms, whereas antisymmetric combination leads to non-bonding. Moreover, symmetric combination give bond energy, which is good improvement over curve 1. Second, Second improvement, screening effect of electrons. The wave function given by equation second is further improved by considering the screening effect of the electrons. When the two atoms come close to each other, the electron of one atom shield the electron of the other atom where the nucleus so that the electron do not feel the full of the charge of the nucleus. The actual charge felt by an electron so it is termed as effective nuclear charge. This will be evidently less than the actual nuclear charge. Now, if we use the value of effective nuclear charge instead of actual nuclear charge and improve the wave equation given by equation second, bonding electron second. Second improvement, screening effect of electrons. The wave function given by equation 6 is further improved by considering the screening effect of the electrons. When the two atoms come close to each other, the electron of one atom shield the electron of other atom from nucleus so that the electron do not feel full charge to the nucleus. The actual charge felt by an electron is termed as its effective nuclear charge. Now, if we use the value of effective nuclear charge instead of actual nuclear charge and improve the wave function given by bonding energy of 365 kilojoule per mole is obtained. Third, ionic character of HH bond. The bond energy of 365 kJ per mole is still appreciably smaller than the experimental value of 458 kJ per mole. This shows that psi still does not give the true orbital wave function for H2. Evidently, further improvement of orbital wave equation is needed. In the first improvement, we have allowed the electrons to exchange, but we have restricted that the electron must change simultaneously. However, it is quite possible to both of the electrons may simultaneously be present close to one nucleus or the other. This means that both of the electrons, first and second, are either present on the atom Ha or on the atom Hb, resulting in ionic character of bonding. The two ionic structure may be represented as Ha Hb and Ha positive Hb negative. Their formation would evidently tend to increase the force of attraction between the two hydrogen atoms, leading to increase in bond energy. It is called mixing coefficient. By knowing delta, we can find out the extent to which the bond is ionic in character. For H2 molecule, the value of lambda is about 0.17. The plot value of energy corresponding to the wave function given by equation 9 is shown in curve V. This gives the bonding of 388 kJ per mole, which is now closer to the experimental value of 458 kJ per mole. With these modifications, the internuclear distance between hydrogen atoms have been found to be 0.75 Armstrong, which is close to the experimental value of 0.74 Armstrong. The differences still persist are due to some complicated electronic interactions. Many more improvements were suggested to get the wave function which give bond energy closer to the experimental value. James and Coolidge used a wave equation consisting of 13 terms and obtained the bond energy of 455 kJ per mole. Colos and Ruthan got the bond energy of 558 kJ per mole, which is same as the experimental value. They used a wave function consisting of 50 terms. This discussion of the arrangement in beyond the scope of the present text. Bond energies and bond lengths of H2 molecules corresponding to the various wave equations are summed up in the table 1. Resonance and resonance energy. The valence bond theory results into concept of resonance. According to the valence bond theory, a molecule of hydrogen cannot be represented by a single structure, which could account for the stability of the molecule. As has been discussed earlier, the actual wave function and the stability of the molecules is obtained by suitable combination of the wave functions of these three structures. In other words, the actual structure of the molecule is not represented by one of the structures but can be represented by the combination of these. The contribution of each structure can be determined by its nature and stability. The actual structure of the molecule is considered as resonance hybrid of these structures. The phenomena is called resonance and the individual structure is called resonating structures and canonical structure. These resonating structures are drawn with double-headed arrows between them. It may be noted that none of the resonating structures have real existence. Also, it does not mean that the actual molecule exists for certain fraction of a time in a form and for another fraction of the time in another form. In fact, the actual structure has pictorial representation. The resonating functions are only a convention way of picturing molecules to account for all the properties of a molecule. The resonance hybrid may be compared with a mule. For example, like a resonance hybrid, a mule has characteristics of donkey and a horse, but at no time it is either of these. When a molecule cannot completely represented by a single structure but its characteristic properties can described by two or more structures, then the true structure is said to be resonance hybrid of those structures. This phenomena is called resonance. The molecule is said to be resonate between the three resonance structures. Resonance energy. As mentioned above, the resonance hybrid is more stable than any of the contributing structures. The extra stability of the resonance hybrid as compared to the most stable of the various resonating structure is called resonance energy. Resonance energy is thus defined as the difference between the actual bond of the molecule and that of the most stable of the resonating structures. Resonance energy is equal to the actual bond energy minus energy of the most stable of the resonating structures. For example, the resonance energy of carbon dioxide is 138 kJ per mole. This means that the actual molecule of the CO2 is about 138 kJ more stable than the most stable structure among the contributing structures. Suppose E1, E2 and E3 are the energies of three resonating structures for a molecule. Their energies are shown in figure 3. It is evident that among these, E3 has the lowest energy. If E naught is the actual energy of the molecule, then resonance energy is equal to E3 minus E0. Rules for writing resonating structure. To explain the characteristics of a molecule, a number of resonating structure may be written. The energies of different resonating structures should be close to actual molecule as possible so that the structure have significant contributions. There are certain rules which permit the selection of the structures which contribute toward resonance. The following are the essential rules for writing resonance structures. Contributing structures should have the same of the atomic position. They should differ only in the position of the electrons. For example, the following two structures of the phosphorus acid are not resonant structure because they have different position of atom in two structure. Second, the contributing structure should have the same number of unpaired electrons. In the above structure, structure 3 is less important than the structure of the 2 because it is seen that 3 unpaired electrons whereas structure 1 and 2 have only 1 unpaired electrons. Obviously, in case structure 3 is unstable because it contains unpaired electrons. Experimentally, it has been observed that benzene does not contain unpaired electron. Third, the contributing structure should not differ much energy. Structure second and first are due to Kekule and are called Kekule structures are structure 3 and structure 4 are due to the Dewar and the Dewar structures. The Dewar structures are less stable and therefore more energetic than the Kekule structures. This is on the account of the long bonds across the ring. It looks highly probable therefore that only one Kekule structure, first and second, are the real contributing structures. Thus, benzene is mainly the resonance hydride of structure first and second. Fourth, contributing structures should be also that negative charge resides on the electronegative elements and positive charge resides on electropositive element. Fifth, in contributing structures like charges should not on adjacent atoms. This means that contributing structure should not be so written that unlike charges reside on the neighboring atom while like charges are separated as apart as possible. For example, resonating structure for nitrous oxide N2O may be written as follows. In case structure 3 is not feasible because it places a positive charge on the electronegative oxygen atom and also has same positive charges on the adjacent nitrogen and oxygen atoms. Sixth, the greater the number of the covalent bonds, the greater is the contribution of the resonating structures. Resonance of some molecules. Let us consider resonance structure of some common molecules. First, hydrogen molecule. The various resonance structure of the hydrogen molecules are discussed below. Second, oxygen molecule. The bonding in O2 molecule is generally represented as below. Second, paramagnetic character. Paramagnetic character due to the presence of two unpaired electrons through the above structure explain the bond of the molecule, yet that they have the account for paramagnetic character of the oxygen. As it is clear of the above structure have unpaired electrons. Thus the above structure do not explain all the properties of oxygen molecule. Third, nitrogen molecule. The nitrogen molecules are the resonating structures. Contribution of structure second and third are relatively less in the above. Fourth, carbon monoxide molecules. First, bond length. In the above structure, there are covalent bonds between carbon and oxygen. The carbon oxygen bond length is experimentally determined by X-ray diffraction to be 1.13 Armstrong. The normal C double bond O bond length is known to be 1.22 Armstrong and C double bond O bond length is 1.10 Armstrong. This means that bond between carbon and oxygen in carbon monoxide is not double. but it's closer to the triple bond. Dipole moment. According to structure third, there is positive charge on oxygen atom and negative charge on carbon atom. Therefore, the molecule should have appreciable dipole moment from oxygen to carbon. But experimentally, the CO molecule has very low dipole moment. This suggests the contribution of the structure second also. Structure second has dipole moment from carbon to oxygen. This reduces polarity of the molecule due to the structure third. Therefore, as expected, carbon monoxide has a very less dipole moment of 0.12. Fifth, carbon dioxide molecule CO2. The simple electronic configuration of carbon monoxide is below. First, bond length. The structure first suggests a double bond between carbon and oxygen. The carbon oxygen bond length in CO2 has been found to be 1.15 Armstrong. The normal C double bond O bond length is 1.22 Armstrong and C double bond O bond length is 1.0 Armstrong. This suggests the carbon oxygen bond in CO2 molecule is between double and triple bond. This means that there must be some contribution for structure second and third which have triple bond also known as carbon and oxygen. Second, dipole moment. Sixth, nitrous oxide molecule. As three structures are polar, structure 3 is unfavorable because it has positive charge on the electronegative oxygen atom and also has electric charge of some sign of the adjacent atoms. Moreover, according to the structure third, the molecule should have appreciably high dipole moment. However, nitrous oxide has a very less dipole moment. This suggests that the contribution of structure third to the real structure is less and the molecule is mainly resonance hybrid of the structure first and second. These have opposing dipole moments and therefore N2O has a very less dipole moment. Seventh, carbonate ion. According to the valence bond theory, the structure of the carbonate ion carrying two negative charges. In this planar structure, there are three carbon to oxygen bonds, two of which are single bonds and the third is a double bond. Evidently, a carbon to oxygen double bond should have been shortened a carbon to hydrogen single bond. It is known from X-ray studies that all three carbon to oxygen bonds in carbonate ion are of equal length, which lies in between the usual single and double bond lengths. This implies that the double bond resulting from sharing of four electrons is not localized between carbon and any other particular oxygen atom. It is spread over all three oxygen atoms. Eighth, azide ion. Limitation of valence bond theory. The main limitations of valence bond theory are: the valence bond theory treatment could be applied successfully only to the few simple systems. In most of the system, the mathematical treatment involved is very difficult and we have to use approximate methods. Therefore, valence bond treatment is unequitable in many systems. Second, this theory assumes that the two electrons of the shared pair contributing of internuclear bond must come from two different atoms. Therefore, the formation of coordination valency should not be explained by this method. Third, it is it is failed to explain the bonding in electron deficient compounds. Fourth, for any molecule or ion, we have to write several resonating structures, and even then, we say that The true structure is none of these, but a resonance hybrid structure of these. It is not possible to write one structure which can explain all structural features of that molecule or ion. Fifth, according to this theory, the atoms in the molecule of oxygen have electronic configuration resembling nu. Direction character of covalent bond. The covalent bond is localized between nuclei of atoms. The strength of these bonds depends on the exchange of ions between the two combining atoms. It is been shown by polling that the strength of covalent bond is proportional to the amount of overlap of the wave function or atomic orbitals of the electron constituting the bond. The bond formed will be strong if there is maximum overlapping of orbital atoms and there is maximum interpenetration of charge densities of the electron involved in the bond formation. Thus, the bond formed by the given orbital will tend to lie in the direction in which the orbital has maximum value. In other words, the covalent bond has directional nature. The directional nature of covalent molecules lead to definite shapes and geometries. The structure and geometries of molecules can be explained on the basis of two theories. First, hybridization. Second, valence shell electron pair repulsion theory, which is also known as Vesper theory. First, hybridization. The concept of hybridization is introduced to explain the shapes of the molecules. We have learned that formation of covalent bonding requires one unpaired electrons, with which of these two overlap orbitals. This means that the number of bonds formed by an atom depends on the some extent on the number of unpaired electrons in the atom. Therefore, in accordance with electronic configuration, beryllium is expected to be inert. Boron with one unpaired electron should be monovalent, and carbon with two unpaired electrons should be divalent. However, in their compound, beryllium is divalent and carbon is tetravalent and boron is trivalent. Therefore, it is not possible to account for the valences of beryllium, boron, and carbon on the basis of simple theory of bonding. In order to explain these anomalies, a new concept known as hybridization was introduced. This can be explained by taking the example of carbon compounds. The ground state electronic configuration of carbon is 1s2, 2s2, and 2p2. The outer electronic configuration of carbon is represented below. There are only half-filled orbitals in the valence shell of carbon. Therefore, its bonding capacity should be 2. However, in actual practice, carbon exhibits the bonding capacity of 4. This can be explained on the basis of promotion concept. The order to explain the bonding capacity of carbon, it was proposed that one of the electrons from 2s filled orbital is promoted to 2p empty orbital, which is in higher energy state. This state of atom is known as excited state and the process is known as promotion. Thus, four half-filled orbitals get formed in valence shell which account for the bonding capacity of 4 of the carbon. The above configuration reveals that all 4 bonds formed by carbon will not be identical. For example, in the formation of CH4 molecule, one CH bond will be formed by overlapping of 2s orbital of carbon and 1s of hydrogen, whereas the other 3 carbon hydrogen bond will be formed by the overlapping of 2p orbital of carbon and 1s orbital of hydrogen. But actually, in the most of the organic compounds such as methane, carbon tetrachloride, all our 4 bonds of carbon are equivalent. The equivalent character of the bonds can be explained with the help of a new concept known as hybridization. The phenomena of intermixing of the orbitals of slightly different energies so it is distribute their energies and give a new set of orbitals of equivalent energies and shape is known as hybridization. Sorry for the page arrangement mistake. So the new orbitals formed as result of hybridization are called hybrid or hybridized orbital. Thus, to form four equivalent bonds ion are 2s and 3 2p of the carbon hybridize and form four new orbitals called sp3 hybrid orbitals. The hybrid orbitals formed have characteristic orientation in space. For example, four sp3 hybrid orbitals orientate towards the four corners of regular tetrahedron. These four orbitals will overlap with one s orbital of hydrogen to give four equivalent bonds. It may be noted that hybridization is not a physical process but it is a mathematical concept of which has been introduced to explain the structure properties of the molecules. Characteristics of hybridization. The number of hybrid orbitals formed is equal to the number of orbitals that gets hybridized. Second, the hybridized orbitals are always equivalent in energy and shape. Third, the hybrid orbitals are more effective in forming stable bonds than the pure atomic orbitals. Fourth, the hybrid orbitals are directed in space in some preferred directions to have stable arrangement. Therefore, the type of hybridization gives the geometry of the molecule. Conditions for hybridization. Only the orbitals present in the valence shell of the atom are hybridized. Second, the orbitals undergoing hybridization should have only a small energy difference. The orbitals, which greatly differ in energy, cannot take part in hybridization. Third, promotion is not only an essential condition prior to hybridization. Fourth, it is not necessary that only half-filled orbitals participate in hybridization. In certain cases, even filled orbitals of the valence shell participate in hybridization. Types of hybridization. There are many types of hybridization. This not only involves s and p orbitals but d orbitals also. First, sp hybridization. In sp hybridization, one s and p orbitals mix and form two equivalent sp hybrid orbitals. The linear geometry of the molecules such as BeCl2, BeH2, BeF2 can be explained on the basis of sp hybridization as described. Beryllium Z is equal to 4 in the ground state has electronic configuration of 1s2 and 2s2. According to the valence bond theory, the formation of covalent bond requires one unpaired electron with each of the two combining atoms. This means that the bonding capacity of an atom depends upon the number of unpaired electrons in the atoms. Therefore, beryllium is expected to show no valency because there are no unpaired electrons in this atom. However, beryllium exhibits divalency in its compounds such as BeH2, BeF2, BeCl2, etc. To account the divalency of beryllium, one of the electron form 2s is promoted to next available vacant 2p as shown. This state of an atom is known as excited state and the process is known as promotion. Now there are two unpaired electrons and beryllium will form two bonds. But the two bonds thus formed will not equivalent because one bond will be formed by the overlap of 2s and 2s of beryllium and 2p of fluorine. while other will be formed by overlapping of 2p of beryllium and 2f of fluorine. But experimentally, it has been observed that both of beryllium fluorine bonds in BeF2 are equivalent. To account for this, it is assumed that one 2s and one 2p orbitals of beryllium hybridize to form equivalent sp hybrid orbitals. These two sp orbitals, trying to remain as far apart from each other as possible, adopt linear arrangement making an angle of 180 degrees between the two orbitals. Now, fluorine atom has the configuration of 1s2, 2s2, 2px square, 2py square and 2pz1. One of the orbitals is evidently half-filled. This half-filled p orbitals of each fluorine atom overlaps with one of the half-filled sp hybrid in beryllium fluoride to be formed. This is represented in the figure above. The bond angle in BeF2 molecule is 180 and the geometry is linear. Second, the sp2 hybridization. In sp2 hybridization, 1s and 2p orbitals hybridize to form three equivalent sp2 hybrid orbitals. Shape of BF3 molecule diagram is shown below. Since boron is trivalent in compound, it is assumed that one of the two s electrons is promoted to next vacant 2p, that is 2py orbital. Therefore, the excited state of boron has three unpaired electrons. Now to form three equivalent bonds, the three orbitals 2s, 2px and 2py hybridize to form trigonal planar arrangement making an angle of 120. The mixing of three atomic orbitals is shown above. These three hybrid orbitals are directed towards the three corners of an equilateral triangle. Each of these sp2 hybrid orbitals has one s character and two third of p character. sp3 hybridization. In sp3 hybridization, 1s and 3p orbitals hybridize to form 4 sp3 hybrid orbitals. This may be illustrated by considering the formation of CH4 molecule. The carbon in its grounded state has only two unpaired electrons. To account for trivalency, it is assumed that one of the two s electrons is promoted to the vacant 2p orbitals, 2pz orbital. To account for equivalent bonds, 1 2s and 3 2p orbitals hybridize to form 4 sp3 hybrid orbitals. Shapes of molecules containing bond pair and lone pairs. If the molecule contains lone pair in addition to bond pairs in the valence shell of all the central atom, the geometry gets distorted. This is because the repulsive interaction between the bonded and the lone pair of the electrons are different. The orbitals of bonded electrons is under the influence of two nuclei and most of the electron cloud is orientated between the nuclei of the two atoms. On the other hand, the lone pair of electrons is under the influence of only one nucleus and therefore its electron cloud is spread out and tends to occupy more space. Since the lone pair is flatter and occupies more space around the central atom, it can interact more and therefore it will repel the electron pair in neighboring orbitals strongly than do the electrons in bonded orbital. Obviously, the repulsion between the lone pairs would be the largest and will be lesser if one of them is bonded pair and least if both are bond pairs. However, it must be remembered that it is the total number of electrons paired in the valence shell of central atom which determine the type of hybridization irrespective of the number of bonded or lone pairs. Due to the presence of lone pairs in the geometry, the regular geometry of the molecule becomes slightly distorted and bond angles change between the normal values in regular geometries. First, stannous chloride molecule. The ground state electronic configuration of the central atom tin is 4d10, 5s2, 5px1 and 5py1. There are 2 electrons in 5p orbital of tin and there are sufficient to form 2 bonds with chlorine atom, and therefore there is no need of promotion of electrons. Then the 3 orbitals of tin atom hybridize to give 3 sp2 hybrid orbitals of equivalent energy as shown. These 3 sp2 hybrid orbitals adopt trigonal planar geometry. One of these hybrid orbitals contain a lone pair of electrons while the remaining 2 contain one unpaired electron each. These two sp2 hybrid orbitals containing unpaired electrons overlap with 2p orbital of chlorine to form SnCl bond. Thus, the central atom Sn is SnCl2 is surrounded by 3 orbitals, each containing a pair of electrons. 2 of these orbitals contain shared pair while the third contains a lone pair of electrons. The geometry of the molecule should have been trigonal planar with the bond angle of exactly 120 degrees. However, on account of the fact that lone pairs show repulsion is greater than bond pair repulsion, there is some distortion in the molecule. The bond angle is slightly less than 120 and the molecule assumes V shape. Second, ammonia. The ground state electronic configuration of nitrogen atom is 1s2, 2s2, 2px1, 2py1 and 2pz1. It contains 3 unpaired electrons in its grounded state. Since nitrogen forms only 3 covalent bonds, there is no need of promotion. These 4 orbitals are hybridized to form sp3 hybrid orbitals. These 4 sp3 hybrid orbitals adopt tetrahedral arrangement. One of these hybrid orbitals contain a lone pair of electrons while the remaining 3 contain one unpaired electron each. These 3 hybrid orbitals overlap with 1s orbitals of hydrogen atom to form 3 NH sigma bonds. Chlorine trifluoride. The central atom chlorine has outer electronic configuration as 3s2 2s5. In the formation of ClF3 molecule, chlorine requires 3 half-filled orbitals to form 3 ClF bonds. This becomes possible by the promotion of one of the electrons of 3p orbital to one of the vacant 3d orbitals. The 5 orbitals hybridize to form 5 sp3 hybrid orbitals which adopt trigonal bipyramidal geometry. 2 of these hybrid orbitals are occupied by lone pair of electrons. The remaining 3 hybrid orbitals contain single electron each and overlap with 2p orbitals of fluorine atom to form 3 ClF sigma bonds. Sixth, xenon difluoride. This molecule has been found to be linear or trigonal bipyramidal with 3 equatorial positions occupied by lone pairs. The outer electronic configuration of the central atom xenon. This is shown in figure 27. In the formation of ZeF2 molecule, one of the 5p electrons is promoted to one of the 5d orbitals. 1 5s 3sp and 1 5p orbital hybridize to give 5sp3 hybrid orbitals which adopt trigonal bipyramidal geometry. 3 of these hybrid orbitals contain lone pair of electrons while the remaining 2 overlap with the 2p orbitals of fluorine to form ZeF bonds. Now the molecule is expected to be distorted trigonal bipyramidal by actually the molecule is linear. This is due to the fact that the 3 lone pairs are present on the equatorial positions. Due to the symmetrical arrangement of the lone pairs around the central xenon, the net repulsion due to these are 0. 7th, xenon tetrafluoride. In case the outermost electronic configuration of the central atom xenon in the grounded state is represented in Figure 28. To account for 4 bonds in the formation of XAF4, 2 of 5p electrons go to the 5d orbital so that there are now 4 unpaired electrons. The 6 orbitals hybridize to form 6 sp3d2 hybrid orbitals which adopt octahedral geometry. 2 of these contain lone pairs of electrons. The remaining 4 contain unpaired electrons which are used in bonding with 4 atoms of fluoride. The geometry of the molecule may be regarded as octahedral with 2 positions occupied by lone pair or square planar. Eighth, iodine pentafluoride. The ground state electronic configuration of the central atom iodine is 5s2, 5px2, 5py2 and 5pz1. To account for 5 bonds of the formation of IF5, 2 electrons from the double filled orbitals are promoted to the next vacant 5d orbitals. Then the 6 orbitals get hybridized to form 6 sp3d2 hybrid orbitals which adopt octahedral geometry. In case one of the position is occupied by a lone pair of electrons, the remaining 5 hybrid orbitals overlap with 2 p orbitals of fluorine atoms to form 1 5IF bonds. Due to the presence of lone pairs, the molecule has distorted geometry. Its actual geometry may be regarded as square pyramidal. BRF5 molecules has also similar geometry. Thus, it may be concluded from the above discussion that the actual geometry of the molecule containing one or more than lone pairs of the electron is different from the geometry which is expected from the type of hybridization involved in the molecule. Sigma and pi bonds. We know that the covalent bond is formed by the overlapping of the half-filled orbitals of the two atoms. First, sigma covalent bond. Second, pi covalent bond. Sigma covalent bond. This type of bond is formed by the end-to-end overlapping of the half 2p or half-filled atomic orbitals. In this case, the overlap along the internuclear axis and the bond is symmetrical about the internuclear axis. The bond can be formed by one of the following methods. First, SS overlapping. Second, SP overlapping. SS overlapping. This type of overlapping involves the half-filled s orbitals of the two atoms. For example, the bond formed between two hydrogen atoms of the H2 molecule in case the 1s orbital of the hydrogen atom overlap to form a sigma bond. Second, sp orbital. This type of orbital involves the half-filled s orbital of one atom and apz orbital of a other atom. For the example, 1s orbital of the hydrogen overlap with two pz orbitals to fluorine to form a sigma bond between hydrogen and fluorine in HF bonds. Third, pp overlapping. This type of overlapping involves half pz orbitals of two atoms. For example, a molecule of F2 is formed by the overlapping of two pz orbitals of fluorine atoms. Second, pi covalent bond. This type of bond is formed by the sidewise overlapping of the two atomic orbitals. The sidewise overlapping can take place when the orbitals have their lobes perpendicular to the molecular axis. For example, two px or py orbitals overlap above and below the internuclear axis to form pi bond. Strength of sigma and pi bond. In case of sigma bond, the orbitals overlap end to end and the extent of the overlapping is large. But the sidewise overlapping to form pi bond is not sufficient. Therefore, sigma bond is strongly bond and pi bond is weak bond. It may be noted that pi bond is present in the addition of a sigma bond in the molecules containing double and triple bonds. For example, oxygen molecule has double bond consisting of sigma and a pi bond. Similarly, N2 molecules contain triple bond, 1 sigma and 2 pi bonds. Let us illustrate the formation of sigma and pi bonds with the help of two examples, ethylene and carbon dioxide. First, formation of ethylene. The trigonal planar geometry of ethylene suggests that in C2H4, Each carbon atom undergoes sp2 hybridization. The carbon atom in the grounded state has the electronic configuration as 1s2, 2s2, 2px1 and 2p51. In the excited state, one of the electrons from 2s is promoted to the nearby 2p orbitals, forming 4 unpaired electrons. The 1, 2s and 2p orbitals get hybridized to form 3 sp2 hybrid orbitals which adopt trigonal planar arrangement. One of these three sp2 hybrid orbitals of each carbon atom overlap with the other carbon atom to form carbon-carbon sigma bond. The remaining two sp2 hybrid orbitals of each carbon form two bonds with hydrogen atoms. On each carbon atom, one p was unhybridized and these p orbitals overlap sidewise forming a pi bond. Thus, in ethylene, the carbon atoms are held together by two bonds, one sigma and another pi. Second, formation of carbon dioxide molecule. The carbon dioxide molecule is a linear and this suggests that the carbon undergoes sp hybridization. The ground state and the excited state of the carbon atom is shown below. The carbon undergoes sp hybridization resulting in two sp hybrid orbitals. These hybrid orbitals overlap with two p orbital of each oxygen to form two sigma bonds. The carbon atom is still left with the two half-filled 2p orbitals. Each oxygen atom was one half filled. These are used for the formation of pi bonds. These are some diagrams. Geometry of some ions. Let us consider geometry of some common ions. Carbonate. The carbonate ion is double charged and two of the oxygen atoms may be considered to have one extra electron. These two oxygen atoms will have only one half-filled orbital each and will therefore form only one bond. The three oxygen will form two bonds because it has two half-filled p orbitals. But in predicting the geometry, any of these orbital structure is sufficient because all convey the same information that there are four bonds. Let us try to account the geometry of carbonate ion on the basis of hybridization. The ground state electronic configuration of carbon contains two unpaired electrons. Since the carbon forms four bonds, one of the electrons from 2s is promoted to the vacant 2p orbital. This is shown in the below figures. One of the half-filled orbitals on the carbon is left for pi bond and remaining three orbitals get hybridized to the formation of sp3 hybrid orbitals. Each of these sp2 hybrid orbitals overlap with the 2p half-filled orbitals of oxygen to form CO sigma bond. The unhybridized 2p of the carbon overlap with the half-filled orbital of the oxygen atom resulting in pi bond between carbon and oxygen bond. Second, nitrate ion. The ground state electronic configuration of nitrogen is 1s2, 2s2, 2px1, 2py1, 2pz1. The nitrogen atom undergoes sp2 hybridization forming three sp2 hybrid orbitals. One of these sp2 hybrid orbitals contain electrons. This suggests that one of the nitrogen-oxygen bonds in nitrate ion is formed. Thus, O negative will form only one sigma bond, while O atom will form two bonds, one sigma and one pi, by the donation of two electrons of nitrogen to oxygen. This is known as coordinate or dative bond. The remaining two sp2 hybrid orbitals, which contain one electron each and sigma with the two other hydrogen atoms, the unhybridized 2p orbital left on nitrogen forms a pi bond with oxygen atom. Perchlorate ion. One of the resonating structure of perchlorate ion is below. The ground state electronic configuration of the chlorine atom is neon 3s2 3p5. In order to account of 7 bonds, 1 3s and 2 3p electrons are promoted to the higher energy vacant 3d orbitals resulting in the 7 unpaired electrons. The 3s and 3d orbitals of chlorine hybridize to form 4th sp3 hybrid orbitals. These orbitals overlap with the four oxygen atoms forming four covalent bonds. Now we are left with the three unpaired electrons in the 3b orbitals of atom. They overlap with the half-filled 2p orbital of the 3 oxygen atom forming the 3 pi bond, one of which each of these oxygen atoms. Fifth, chlorate ions. The ground state electronic configuration of chlorine ion is neon 3s2 3p5. Since chlorine is to form 5 bonds and 1 3s and 3p electrons are promoted to the higher vacant 3d orbitals forming 5 unpaired electrons, chlorine undergoes sp3 hybridization, forming 4 sp3 hybrid orbitals. The sp3 hybrid orbitals adopt tetrahedral geometry in which the position of the occupied by lone pair of electrons. This accounts for the pyramidal structure of ClO3 negative ion. The remaining 3 sp3 hybrid orbitals form 3 sigma covalent bonds in which 3 oxygen atoms are present. The unhybrid orbitals on chlorine atom form 2 pi bonds with 2 oxygen atoms. Structure of ion containing one or more covalent bonds. The structure of ion containing coordinate bond can be described on the basis of hybridization. For this, vacant orbitals equal to the coordinate bonds are also hybridized. The coordinating group donates a lone pair of electrons to the vacant hybrid orbitals. First, Bf4 negative ion. The ground state electronic configuration of boron atom is 1s2 2s2 2p1. One of the electrons from 2s2 is promoted to the vacant 2p orbitals resulting 3 unpaired electrons. The 2s and 3 2p orbitals of boron hybridize to form 4 sp3 hybrid orbitals in which one orbital is vacant. The 3 hybrid orbitals which contain 1 electrons each are used for the formation of 3 F atoms. One fluorine ion donate a lone pair of electrons to the vacant sp3 hybrid orbital forming one coordinate bond. Second, Pf6 negative ion. In this ion, there are 5 sigma bonds and 1 coordinate bond. The ground state electronic configuration of phosphorus atom is neon 3s2 3p3. To account for the 5 covalent bond, one of these, the 3 electrons, is promoted to the 3d orbital so that there are 5 unpaired electrons. The 6 orbitals hybridize to form 6 sp3d2 hybrid orbitals which adopt the octahedral geometry. 5 of these contain 1 electrons, each are used for the bonding with 5 F atoms. One fluorine ion donates a lone pair of electrons to the vacant hybrid orbitals. Third, effect of electronegativity on the shapes of the molecule. The electronegativity of the atom is present in the molecule has also important effect on the shape of the molecules. First, effect of change of electronegativity of the central atom. Take the example of hydrides of group 6 element. The hydrides H2O, H2S, H2SC and H2TE have 4 electrons pairs around the central atom, but their bond angle decreased in order to H2O, H2S, H2SE, H2TE. This may be easily explained in the terms of electronegativities of the central atom as below. In the hybrid orbitals of 6 elements, the central atom involves sp3 hybridization and is surrounded by 4 electron pairs. 2 lone pairs and 2 bond pairs due to the larger lone pair repulsions. The bonded electrons pair are formed closer to each other. Therefore, the bond angle decreases from normal tetrahedral angle of 109.5 degree. Now, as we move down the group from the oxygen to tellurium, the size of the central atom goes on increases and electronegativity goes on decreases. Consequently, the position of the bond pairs of electrons shift more and more away from the central atom in moving from H2O to pairs of electrons shift more and more away from the central atom is moving from H2O to H2TE. Second, effect of change of electronegativity of the bonded atom. This can be explained on the basis of electronegativity of the atom attached to the central atom. In these molecules, P involves sp3 hybridization forming 3 sigma bonds. One position is occupied by lone pair. The geometry may be described as pyramidal as we move from PF3 to PI3. The electronegativity of the atom attached to the central phosphorus atom goes on decreasing. As a result, the bonding pair moves closer to the central atom as shown. For example, as shown in figure, the bond pair of PF3 is away from P than the bond of Cl3. Therefore, the repulsion between the bonding pairs increase, and hence bond angle decreases. Valence shell electron pair repulsion theory, which is also known as VSEPR theory. Valence shell electrons pair repulsion theory is the simplest theory for predicting the geometries of the molecules. It is based on the repulsive interaction between the electron pairs in the valence shell. This theory was proposed by Sedgwick and Powell in 1940, was finally developed by Gillips and Nyhorn. According to this theory, the shape of the molecule can be determined by the number of electron pairs in the valence shell of the central atoms. These electron pairs experience electrostatic repulsion from one another, and bonded carbon atoms in a molecule adopt that particular arrangement in space around the central atom which keeps them on the average as far as possible. Postulates of the VSEPR theory. First, the geometry of the molecule depends upon the number of the valence shell electron pairs around the central atom. In the formation of bond, the central atom shares its valence electrons with the surrounding atoms. However, in the certain cases, all the valence shell electrons may not take part in the bond formation. The electrons left in the valence shell without forming bonds exist as lone pairs. For example, in methane, carbon uses all 4 valence electrons in forming 4 bond pairs. On the other hand, in water, the central atom has 6 valence electrons. The hydrogen atom shares 2 of these 6 valence electrons in the bond formation, leaving 4 electrons as 2 lone pairs. Thus, there are 4 bond pairs around the carbon, while oxygen in water has 2 bond pairs and 2 lone pairs around it. Electron pairs tend to repel one another because their electron clouds are negatively charged. As a result, the electron pairs try to stay as far apart as possible to acquire a state of minimum energy or maximum stability. Third, repulsion between the lone pair and the lone pair of electrons is different than between the bond pairs or one lone pair and one bond pair. The presence of lone groups in the addition to bond pairs will result in certain distortions in the regular geometry of the molecule. Fourth, repulsive forces decrease sharply with the increasing angle between the electron pairs. They are strong at 90 degree, much weaker at 120 degree, and the weakest at 120 degree. Regular and irregular geometries. The molecule in which the central atom is surrounded only by similar bonded electron pairs will have regular geometries, while those in which the central atom is surrounded by the bond pair as well as lone pairs will have irregular geometries. For example, the molecules such as CH4, BF3, PF5, sp6, etc. have regular geometries because the central atoms in these molecules are bonded to similar atoms and there are no bond pairs in these molecules. On the other hand, the molecules such as CH2, Cl2, Cl3, etc., in which the central atom is bonded to different atoms, and the molecules such as NH3, H2O, have lone pairs as well as bond pairs have irregular geometries. Depending upon the number of electron pairs, the molecule have different geometries. It may be noted that the presence of lone pairs disturbs the geometry as already discussed in the case of hybridization. Applications of VSEPR theory. VSEPR theory provides a simple approach to predict the shape of the molecule. These results obtained on the basis of this theory are quite in agreement with those obtained from hybridization concept. This theory is very simple to use. In this theory, no distinction is made between s and p electrons. We take into account only the number of electrons pair present in the valence shell of the central atom. The basic point is that electron pairs try to remain as far apart as possible to get a stable of stability. First, ammonia molecule. In ammonia molecule, the central nitrogen atom has 5 valence electrons. There, 3 of these valence electrons share electrons with the 3 hydrogen atom, forming the 3 bond pair around the nitrogen atom. The remaining 2 electrons are present as a lone pair. Thus, in ammonia, nitrogen is surrounded by 4 electron pairs, 3 bond pairs, and 1 lone pair. Therefore, 4 electron pair adopt tetrahedral geometry, but the bond angle will not be 109.5 degree because one of the electron pairs around the nitrogen is a lone pair. As already discussed, lone pair bond repulsion is more than bond pair repulsion. As a result, the lone pair of electron will repel the bond pair strongly and bond angle decreases to 107 degree. The geometry of the ammonia molecule is regarded as pyramidal. Second, hydrogen molecule. In case of water, the central atom has 6 valence electrons. In the formation of water molecule, the electron form 2 bond pairs with the hydrogen atom after leaving 4 electrons as 2 lone pairs. The 4 electron pairs around the central atom adopt tetrahedral geometry. However, the bond pair angle of water is not 109.5 degree but it is 104.5 degree. The distortion is due to the presence of 2 lone pairs because it causes larger repulsion. Third, hydronium ion. In case the central oxygen atom has 6 valence electrons. In the formation of H3O positive, the electrons form pairs with 2 H atoms and 1 hydrogen ion atom, leaving 2 electrons as 1 lone pair. It may be noted that there is one coordinate bond between lone pair of oxygen atom and hydrogen ion. The 4 electrons pairs around the central atom adopt tetrahedral geometry. However, it is due to the presence of lone pair, the geometry is distorted and the bond angle is normal tetrahedral angle of 109.5 degree because the larger lone pair repulsion then the bond pair repulsion, the bond angle decreases to about 107 degree. Molecular orbital theory. Molecular orbital theory was developed by Hunt and Mulliken in 1932. The basic idea of molecular orbital theory is about the atomic orbital of individual atom combined to form molecular orbitals. The electron in the molecules are present in those molecular orbitals which are associated with several nuclei. These molecular orbitals are filled in the same way as the atomic orbitals are filled in atoms. Molecular orbital theory is based upon the following assumptions. First, a molecule is considered to be quite different from the constituent atoms. All the electrons belonging to the atom constituting the molecule are considered to be moving along the entire molecule under the influence of all the nuclei. Just like an atom, molecules has orbitals of definite energy levels. These orbitals are molecular orbitals. The molecular orbitals are formed when the atoms to be bonded come closer together. The atomic orbitals of these atoms merge into nuclear orbitals. Thus, the molecular orbitals are associated with nuclei of all the bonded atoms in a molecule. The shape of the molecular orbitals depend upon the shape of the combining orbitals. Linear combination of atomic orbitals. According to the molecular orbital theory, the molecular orbitals are formed by the linear combination of atomic orbitals of the atoms which form the molecule. The linear combination means the simple addition or subtraction of the wave fraction of the atomic orbitals. For example, consider a hydrogen molecule consisting of 2 atoms labeled as HA and HB. Let the wave function for the electrons in the atomic orbital of 2 atoms A and B is psi A and psi B, respectively. When these atomic orbitals are brought closer, they combine to form nuclear orbitals. The wave function psi for electron in the field of nuclei of atom A and B may be written as a suitable linear combination of wave function psi A psi B. In case of homonuclear diatomic molecules such as H2, these atomic orbitals must contribute equally to the molecular orbitals. Thus, in case of H2 or any other homonuclear Diatomic molecule, the weight of Ca and Cb must be same. The orbital associated with Psi is called bonding molecular orbital, whereas the orbital associated with Psi star is called antibonding molecular orbital. Thus, the number of molecules orbital present is equal to the number of orbitals combined. The physical structure bonding and antibonding molecular orbitals can be obtained by considering the atomic orbitals. To illustrate these, we may take the combination of one s orbital of one hydrogen atom with one s orbital of second hydrogen atom to form two molecular orbital in hydrogen molecule. As discussed, there are two ways of combining atomic orbitals. The molecular orbital formed by the addition of overlapping of one s orbitals. In case of the 1s orbitals of hydrogen, the wave function is positive and the two orbitals combine to form a molecular orbital, which is also a positive in all the designs of the space. It is clear from the figure that the design between the two nuclei where the two 1s atomic orbital overlap has high electron density. Such a molecular orbital is called bonding molecular orbital. In these orbitals, there is a plane of zero electron density between two nuclei. This is called nodal plane. As it is clear, the electron density is thus molecular orbital is concerned in the regions where each nuclei. In other words, if it does not contribute to the bonding of the HBA and HB do not form bonds, therefore the resulting molecular orbital is called anti-bonding molecular orbital. These bonding and anti-bonding molecular orbitals are labeled as sigma 1s and sigma star 1s. The 1s indicates that the molecular orbital is formed from 1s atomic orbital. The asterisk is used to represent antibonding. The sign sigma identifies that the orbital is symmetrical about the molecular axis. Relative energies of bonding and anti-bonding molecular orbitals. We have learned that in case of bonding molecular orbital, the attraction of both nuclei for the electrons is increased. This results in lowering of energy. In case the antibonding molecular orbital, the electron tries to give away from the nuclei and this responds to the repulsive state. The energy of this orbital will be higher. The relative energies of bonding and anti-bonding molecular orbitals with atomic orbitals can be represented as below. Thus, the bonding orbital is stabilized relative to the energy of isolated atoms and anti-bonding molecular orbital is destabilized relative to the individual atoms. Further, it may be noted that the bonding MO is stabilized to the same extent as anti-bonding molecular orbital is destabilized in the case of homonuclear diatomic molecules. There is difference between bonding and anti-bonding molecule orbitals. Bonding molecular orbitals. First, bonding molecular orbital is formed by the addition of overlap of atomic orbitals. Second, it has greater electron density in the region where between the two nuclei of bonded atoms. Third, the force in this orbitals tend to bring the two nuclei of atoms together. Therefore, the electrons in the bonding molecule orbital to attraction between the two atoms. Fourth, it possesses lower energy than the isolated atomic orbitals. Anti-bonding molecular orbitals is formed by the subtraction of the overlap of atomic orbitals. It has lesser electron density in the region between the two nuclei of the atoms. The forces in this orbital push the electron nuclear apart. Therefore, the electron in anti-bonding molecular orbital contribute to repulsion between the atoms. It possesses higher energy than the isolated atomic orbitals. Combination of 2s and 2p atomic orbitals to form nuclear orbitals. Combination of 2s orbital like 1s 2s are also combined by the addition of subtraction of overlap to form bonding and anti-bonding molecular orbitals. These are labeled as sigma 2s and sigma star 2s. They differ from sigma 1s and sigma star 1s molecular orbitals with regard to the size only. Combination of 2p atomic orbitals. Now let us consider the combination of 2p atomic orbitals. There are 3p atomic orbitals, namely 2px, 2py and 2pz, which are directed in space along the xyz coordinate axis respectively. By convention, we can assume z-axis as the internuclear axis. The x and y axis would then perpendicular to the internuclear axis. Conditions for the combination of atomic orbitals. We have learned that molecular orbitals are formed by the effective combination of atomic orbitals. But all types of orbitals cannot combine with each other. The following are the main conditions for the effective combination of atomic orbitals. First, the energies of AOs involved should not be differed much from one another. The combining atomic orbitals should not differ much in energies. For example, in case of homonuclear diatomic molecules of type A2, 2s orbital of one atom can combine with 2s orbital of another atom. But 1s orbital of one atom cannot combine with the 2s orbital of another atom. Second, the atomic orbital combine only when if they overlap to the considerable extent. The extent of overlap between the atomic orbitals of two atoms should be large. Third, the combining atomic orbitals should have the same symmetry about the internuclear axis. In other words, in order to term bonding and anti-bonding molecular orbitals, either the symmetry of the two atomic orbitals must remain unchanged when the rotating about the internuclear axis, or both atomic orbitals must change symmetry in an identical manner. For example, a 2s orbital of one atom can combine with 2s orbitals of another atom, but it cannot overlap with 2px and 2py orbital of another atom. Energy level for molecular orbitals. The relative energies of molecular orbitals depend upon the following two factors: the energies of atomic orbitals combining to form molecular orbitals. Second, the extent of overlapping between the atomic orbitals. First, the greater the overlap, the more the bonding orbital is lowered and the anti-bonding orbital is raised in energy relative to atomic orbitals. For example, the overlapping in case of sigma orbital is more than the in pi orbital. Consequently, the energy of sigma 2pz is lower than the energy of bonding pi 2px or pi 2py molecular orbitals. For example, molecules formed from first row elements, we have drawn the energy level diagram as shown in figure 58. In case sigma 1s is lower in energy than sigma star 1s molecular orbital. However, when 2s and 2p orbitals are involved, 8 molecular orbitals are formed. Here is the energy level diagram. However, experimental evidences for some diatomic molecules have shown that above sequence of energy level of molecular orbitals is not correct for all molecules. It has been observed that in case of homonuclear diatomic molecules of second row elements, this order is not correct for molecular orbitals onwards. On the other hand, for molecules up to N2, molecular orbitals is higher in energy than pi 2px and 2py molecular orbitals. The change in the sequence of the energy level of the molecular orbitals is due to the possibility of mixing 2s and 2pz atomic orbitals. Rules for filling molecular orbitals. The following rules are followed for filling up molecular orbitals with electrons to write molecular orbital configurations. First, the molecular orbital having lowest energy is filled first, thus in accordance with the above principle as already discussed. Second, each molecular orbital can accommodate a maximum to 2 electrons having opposite spins. This is in accordance with Pauli exclusion principle. If there are two molecular orbitals of the same energy, the pairing of electrons will occur only after each orbital of same energy has one electron. Thus is accordant with the Hund rule. Electronic configuration and molecular behavior. Molecular orbital energy level diagrams give very valuable information in regarding the behavior of molecules. The important conveyed by the electronic configuration of the molecules. First, stability of the molecule. We have learned that the electron in the bonding molecular orbital contribute to the attraction between the atoms and thereby help in the formation of the bond. On the other hand, the electron in antibonding molecular orbital contribute to repulsion between the atoms and therefore oppose the formation of the bond. Thus, the electron in bonding molecular orbital with stability to the molecule, whereas those in antibonding molecular orbital will decrease in the stability. Second, bond order. It is defined as the number of covalent bonds present between the two bonded atoms in a molecule. Bond order can be calculated from the number of electrons in bonding and antibonding orbitals. Information conveyed by bond order. The bond order conveys the following important information. If the value of the bond order is positive, it indicates a stable molecules, and if its values of bond order is 0, it means that the molecules is unstable. Second, the stability of the molecule is measured by the bond dissociation energy. But the dissociation energy is directly proportional to the bond order. For example, nitrogen molecule with bond order equal to 3 has larger bond dissociation energy than oxygen molecule. Dissociation energy with the bond order equal to 2. The positive value of bond order indicates that the molecule is stable. The presence of unpaired electron in the molecule indicates that if it is paramagnetic molecule, the stability of the ion as well as paramagnetic character have been confirmed experimentally. The bond length of hydrogen ion is larger than the hydrogen molecule, while its bond dissociation energy is less than that of H2 molecule. This clearly supports the fact that the bond in H2 positive is weaker than the H2 molecule. Third, hypothetical helium molecule. Each helium atom which has 2 electrons in one s orbital and therefore there are 4 electrons to accommodated in helium molecule. Now each molecular orbital can accommodate only 2 electrons. Therefore only a pair of electrons can be accommodated in sigma 1s molecular orbital. The other two electrons enter in sigma star 1s molecular orbital. The electronic configuration for the helium is sigma 1s2 and sigma star 1s2. The zero bond order value indicates that there is no net bonding in He2 molecule should not be formed. In fact, there is no experimental evidence for the existence of this molecule. Fourth, helium molecule ion. This molecule contains 3 electrons. The 2 electrons enter sigma 1s molecular orbital and the third electron goes into sigma star 1s molecular orbital. The molecular orbital energy level diagram is shown in figure 72. The value of bond order indicates that helium is stable. Its bond dissociation energy has been found to be 242 kJ per mole. Fifth, hypothetical HHE molecule. The hypothetical HHE molecule is formed by the combination of one H atom and one helium atom. Therefore, the molecule has 3 electrons. The molecular orbital configuration of HHE molecule is sigma 1s2 sigma star 1s1. Diatomic molecules of second row elements. In these elements, the 1s orbitals are completely filled. These four electrons will completely fill the 1s and sigma star 1s molecular orbitals. Therefore, these does not contribute to bonding. Therefore, to calculate the bond order, one of the valence shell are considered. For simplicity, in the formation of molecular structures of these molecules, the letter Kk are generally used to denoted by the fully filled inner shells. Sixth, lithium molecule Li2. The electronic configuration of lithium is 1s2 2s1. There are 6 electrons in lithium molecule. The 4 electrons are present in the key shells and there are only 2 electrons to accommodated in the outermost orbitals. These 2 electrons go in the bonding sigma 2s molecular orbital, which has lower energy, and the anti-bonding molecular orbital remains empty. Moreover, the inner electron 1s2 electrons of 2 lithium atoms cause repulsion between the atoms, therefore they do not allow them to come closer. Beryllium molecule. The next element, beryllium, has electronic configuration of 1s2 2s2. In the formation of a diatomic molecule, evidently 2 outer electrons of each atom, 4 in all, have to be accommodated in the molecular orbitals. 2 of these go in the bonding orbital while the other 2 give into the anti-bonding orbital. The molecular orbital electronic configuration is Kk sigma 1 2s2 and sigma star 2s2. The bond order is 0. Heteronuclear diatomic molecules. In heteronuclear diatomic molecules, two different atoms are bonded together. The principles involved in the distribution of electrons are the same as discussed earlier. However, the molecule orbital ray diagram may not be symmetrical as case of homonuclear diatomic molecules. For examples, let us consider a molecule AB in which B is more electronegative than A. In above, where Ca and Cb are the coefficients which have the weights of wave function for the atom A and B respectively. The value for the constant Ca and Cb will be different for these atoms. The atomic orbitals of A and B are not placed in the same level since B is more electronegativity than A. Its orbitals are lower energy and are therefore placed lower than the corresponding atomic orbitals of A. Due to the difference in the electronegativity of the atom, the bonding molecular orbital are closer to the more electronegativity of the atoms. On the other hand, the anti-bonding molecules are nearer to the less electronegative atom. This is the main difference in the molecular orbital diagram for homonuclear and heteronuclear diatomic molecules. Thus, it may be noted that for drawing MO orbital diagram for heteronuclear diatomic molecules, the same molecular orbitals are found as in case of homonuclear diatomic molecules, but the bonding molecular orbitals are shown closer to the more electronegative atom, and the anti-bonding molecular orbitals are shown closer to less electronegative atom. First, boron. Boron oxide. The electronic configuration of boron are 1s2 2s2 2p1 and for oxygen it is 1s2 2s2 2p4. Here are some examples. Hydrogen chloride HCl molecule. The molecular orbital diagram for HCl molecule is also similar of the HF molecule. The electronic configuration of H and Cl are 1s1, 1s and 1s1, 1s2, 2s2, 2p6, 3s2, 3p5 respectively. In the formation of HCl molecule, only the 3pz orbital of Cl would combine effectively with the 1s electron of the hydrogen atom. The 3px and 3py orbitals of Cl cannot combine with s orbital due to the symmetric considerations. These orbitals remain as such and are regarded as non-bonding molecular orbitals. The 3p-Z orbital of chlorine combines with 1s orbitals of hydrogen to form one bonding molecular orbital and one anti-bonding molecular orbital. Comparison of valence bond and molecular orbital theories. The valence bond theory and molecular orbital theory are the two basic approaches to explain the structure and bonding in molecules. Similarities of valence bond and molecular theories. First, both of theories are approximations. Second, both of the theories take into the account the overlapping of atomic orbitals. The strength of the bond depends on the extent of overlapping and interaction. Third, the basic principle in both the distribution of electrons are similar. Thus, an orbital, whether atomic or molecular, cannot have more than two electrons. They are filled in order of increasing energy. If there are more than one vacant orbitals having the same energy, they would be filled singly. Fourth, in covalent bond formation, the essential interaction according to both of the theories is the sharing of bonding electron density by the both nuclei. Both the theories predict the concentration of electron density between the nuclei. Fifth, both the theories predict that for bonding the atomic orbitals must overlap and have approximate symmetry about the molecular axis. Sixth, both the theories account for the directional nature of covalent bond. Point of differences: valence bond theory and molecular orbital theory. First, molecular orbital theory. This theory starts with the nuclei of the constituent atoms. It treats the nuclei of the molecule as a polycentric and thus constructs the molecular orbitals. The atoms lose their identity. It does not involve the concept of resonance. The molecular orbital theory overestimates the contribution of the ionic terms in its total wave fraction. It explains the paramagnetic nature of O2 molecule. Valence bond theory. It starts with the individual atoms and considers the interaction between them. Electrons in the molecules are localized if they are present in isolated atoms. Third, the atoms retain their individual identity. Resonance is an integral part of valence bond theory. For the most of the molecule, valence bond theory underestimates the ionic term and does not give much importance. It cannot explain the paramagnetic nature of O2 molecule. Bonding parameters. Covalent bonds are characterized by the certain parameters such as bond length, bond angle, bond order, and bond energy. First, bond length. It is defined as the average distance between the centers of the nuclei of the two bonded atoms in a molecule. It is determined with the help of X-ray diffraction analysis if the substance is obtainable in crystalline form. Otherwise, the bond length are determined with the help of spectroscopy or other techniques. It is usually expressed in angstrom units or picometer. For example, the bond length between the two hydrogen atoms in a hydrogen molecule is 0.74 angstrom. The bond length of the some simple bonds are given in table below. It may be noted that the bond length decreases with increase in bond multiplicity. Thus, carbon-carbon bond length is shorter than carbon double-bond-carbon bond in which in turn is shorter than C single bond with carbon. This is expected because the increase in atomic orbital number in the group, the distance of the valence electron from the nucleus increases successively with the addition of new shell. In other words, the size of the atom increases along a group and consequently the distance between the bonding nuclei increases. Second, bond angle. It may be defined as the average angle between the atomic orbitals containing bonding electron pairs around the central atom in a molecule. It is expressed in degree, minute, and second. Bond angle gives an idea about the distribution of orbitals around the central atom in a molecule and therefore determines the shape of the molecule. 3. Bond order. Bond order is defined as the number of covalent bonds present between two bonded atoms in a molecule. The bond orders of 1, 2, and 3 correspond to single, double, and triple bonds. For example, in hydrogen, similarly, oxygen molecule have the bond order of 2 and nitrogen molecule has bond order of 3. Bond energy, bond dissociation energy. We have learned that when a bond is formed between the atoms, energy is released. This means that the bonded atoms have lesser energy than the separated individual atoms. Obviously, the same amount of energy will be needed to break the bond. This is called bond dissociation energy and is to measure of the bond strength. It may be defined as the amount of energy required to break 1 mole of bonds of the particular type between the atoms in a gaseous state. It is generally expressed in terms of kilojoule per mole. For example, the bond dissociation energy of HH bond in hydrogen molecule is 458 kJ per mole. Similarly, the bond dissociation energy of Cl and Cl bond in Cl2 is 242.5 kJ per mole. Bond dissociation energy depends upon the two factors. Size of bonded atoms. The smaller the size of the bonded atoms, the stronger is the bond. Consequently, larger is the value of dissociation bond energy. For example, the bond dissociation energy of HH bond is larger than the bond dissociation energy of CCl bond. Second, bond length. Bond length. Shorter the bond length, the larger is the value of bond energy. For example, CC bond is larger than C double bond with C bond length. Consequently, the bond dissociation of energy of C single bond with C is smaller than the C double bond with C. Percentage ionic character. As already discussed, most of the bonds have intermediate character between ionic and covalent bonds. The ionic bond has some covalent character and the covalent bond has some ionic character. When the degree of ionic character depends upon the atoms forming the bond. When a covalent bond is formed between two similar atoms, the shared pair of electrons lies midway between the nuclei of both the atoms because the atoms have tendency to attract the bond pair of electrons. This tendency of an atom to attract the shared pair of electrons towards itself is known as its electronegativity. In other words, in homonuclear diatomic molecules, the electron pair is equally distributed between the two atoms. Such as covalent bond is known as non-polar covalent bond. In case the covalent bond is formed between two dissimilar atoms, one of which has larger value of electronegativity. The bonding pair of electrons is displaced toward the more electronegative atom. Due to the unequal distribution of electron density, the more electronegativity atom require a partial negative charge, where the less electronegative atom acquires a partial positive charge. Thus, a covalent bond develops a partial ionic character as a result of the difference of the electronegativities between the atoms comprising the bond. Such a bond called polar covalent bond. For example, the bond between hydrogen and chlorine atoms in HCl molecule is polar because the shared electron pair is displaced more towards chlorine atom, which is more electronegative. Dipole moment. It has been discussed earlier that the covalent bond between two atoms having a difference of electronegativity acquires a partial polar character. Thus, the two charge ends of the polar bond behave as electrodipoles and the degree of polarity is expressed in terms of dipole moment. Dipole moment. It is defined as the product of the magnitude of charge on any of the atoms and the distance between them. Since the charge E of the order of 10 की power minus 10 and d is the order of 10 की power minus 8 centimeter. Then mu, which is the product of d and e, is the order of 10 की power 18 minus 18. This is a unit called dB and it is represented by d. Dipole can be determined experimentally and the value can be given by the idea of the polar character of a molecule. It is a vector quantity and it has a direction as well as magnitude. The direction of the dipole moment is usually represented by an arrow pointing the positive center toward the negative center. Dipole moment and percentage ionic character. The dipole moment can help us to calculate of ionic character or magnitude of the fractional charge. The percentage of ionic character is obtained from the ratio of the observed dipole moment to the dipole moment for the complete electron transfer. Consider, for example, HCl assuming 100% ionic character, the dipole moment of the molecule whose bond length is 1.275 angstrom. The observed dipole moment of HCl has been found only 1.03 dB, showing thereby that the molecule of HCl is mostly covalent and only partially ionic. The ratio of the observed dipole moment to the dipole moment of 100% ionic character gives a measure of the degree of ionic character. Thus, the percentage can be calculated experimentally. Measure dipole moment and bond length. The dipole values and the percentage ionic character for hydrogen halides are below. Ionic character and electronegativity difference. The ionic character of covalent bond also depend upon the electronegativity difference of the two bonded atoms. The greater the difference in the electronegativities of the bonded atoms, the higher ionic character of the bond. As calculated above, the electronegativity difference between the H and Cl atoms in HCl and the bonded is approximately 17% ionic. Carrying out similar calculation with other hydrogen halides, it was observed that the bond in Hi was electronegativity difference of 0.4 and it is only 5% ionic. It has been observed that when the electronegativity difference is 1.7, then the bond is 50% ionic and the 50% covalent. As the electronegativity difference increases, the bond becomes more and more ionic. Following plot a graph between electronegativity and difference in the percentage error. From plot, he gave the following empirical relation, where Xa and Xb are the electronegativities of the atoms A and B respectively, and Xa is much greater than Xb. With the more value data available, Hannay and Smith gave more simple equation for determining the percentage ionic character from electronegativity of the two atoms. The Hannay and Smith relationship percentage is 16 bracket Xa minus Xb plus 3.5 Xa minus Xb square, where Xa and Xb are the electronegativities of the bond atoms of A and B respectively. Xa is greater than Xb here. Thank you.